Right, to do a problem like this, we're interested in the sign of delta S and the sign of delta H. Now the equation that we're using here is going to be delta G naught equals delta H naught minus T delta S naught. We're not interested in exact numbers here, we're just interested in what the signs of each of these is going to be so that we can predict the sign of delta G naught. So the first thing we can do is we can look at this and we see endothermic. Now endothermic is going to have a delta H, which is positive. Now endothermic means that we have a reaction type situation. So this is a reaction path way down here. And this is energy. And the situation is going to look like this. No, it isn't. It's going to look like this. There we go, that's better. So that means we have a positive delta H, because the difference in, this is the products, this is the reactants, and the sum, delta H is going to equal the sum of the heats of formations of the products minus the sum of the heats of formation of the reactants, which means that we're going to have a big value minus a small one, which is going to be a positive value. So the reverse is true, of course, if we're dealing with an exothermic process. But what we're interested in here is the fact that delta H is positive. Now the other thing we're going to have to do here is figure out how many ions we have on each side, so we can figure out what the sign of delta S is. If we've got 6 LiClO4, if I do a picture of that, it would look like this. I can put the charges on. I don't really need the charges, but I'm going to put them on anyway because I like the charges on the ions. That's 12 ions in total if you count them up. So that's how many ions we have on this side. Remember that the solid here, that doesn't split into ions, so we don't count that. So that's going to be 12 ions on the reactant side. Now on the product side, we've got 2 FeClO4 3. If I drew a picture of that, that's 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 ions there. And we also have the 2 Li2CrO3s as well. I'll squeeze them in down here. Yes, 3 of those, 3 Li2CO3s. Now if you count those up, you'll see there's 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 ions in total over there on the Li2CO3s. So we count these up, and in total on the product side, we've got 8 and 9, that's 17 ions. So you can see there's more ions on the product side than there are the reactant side. So remembering that the delta S is going to be decided by the sum of the S naught of the products minus the sum of the S naught of the reactants, you can see that it's going to be 17 minus 12, which is 5. So that's a positive number. That tells us there's been an increase in entropy going from the reactants to the products. So the sign of delta S is going to be positive. Okay, so I'm going to delete this stuff that we're seeing here. And we're going to investigate what happens now with the sign. So that's going to be positive, and that's going to be minus T times a positive number. Now T is always going to be positive as well because that's a Kelvin temperature. That's always going to be positive by definition. Now what I want you to see here is that they have the same sign. And what that means is that if we have a small temperature, delta G will be positive. And it will be negative at a high temperature. Now the way I'm seeing this, if this is positive and we're subtracting a smaller number from it because T is small, let's say we make T 0 for example, then you can see that delta G will end up being positive. But you can also see a case that if T was high enough, this number could be bigger than this number, and we would end up getting a negative value because this number ends up being subtracted from the positive number that we're seeing here.